Hello, everybody. I'm Pablo Dubuer, and this is a talk about a little bit of career advice, if you can we can say so. So there is this little ebook. It's only 70 pages long, published a decade ago by the MIT Center of Digital Business, where the authors start looking at the effect of technification in the recent erosions of jobs. And one of the, I mean, we all have, we all know that as new computers and machines become available, some jobs go away. What is interesting about the current process is that the normal idea is that the jobs that go away are the less skilled jobs. Well, the authors found out that that's not the case. Actually, the distribution of job losses follows a U-shaped pattern. Yes, and that means that it's not the less skilled workers that are losing their jobs, are the ones that are somewhat skilled around the middle. So for us, data scientists, what that means is that if a task you are doing seems to be automatable, most probably will be automated. Yes, AUTOML, it's going to be the big push for the 2020s in machine learning, is going to reduce significantly the number of data scientist jobs. Yes, and so in a way, the automation is making all our jobs at risk. And how can we maintain our jobs then? Well, what the book poses forward is that the future is hybrid. Yes, that the future of employment is a partnership between humans and computers to solve problems and create value. And as an example, currently, translating documents is no longer an activity undertaken exclusively only by a human. It's a partnership where a computer makes a first pass, and then the human translator can get paid by the number of edits they do to the computer translation. Of course, things like translating music or poetry or legal translations still require 100% human work, but the bulk of the job is done with this type of arrangement. So the whole point of this talk is we have a lot of discussion, particularly in the symposium, about process, about methods, yes, but you have to make your human side count, yes. In that sense, you have to go for things that the algorithms themselves cannot do. In a way, if you want to stay employed, you can increase your skills and go for the algorithms and try to design new machine learning algorithms or focus on data engineering pipelines. Yeah, these things are seldom done in companies, although some companies have very complex data engineering pipelines, and you can go in that direction. Instead on this talk, what I'm talking is about going for the data itself, that is focusing in the domain and improving the input, or going for the problem and focusing on the business side and improving the output. Now, I'm a very technical person. This talk, even though the topic is quite soft, I will try to put these concepts into actionable technical advice that we can all follow. As I mentioned, well, my background is technical. I have a PhD from Columbia University in New York City. My thesis was on weakly supervised learning for text generation. From there, I joined IBM Research, and I was part of the original team that built the deep QA system that with the Jeopardy champions. And after IBM, I have been consulting for almost a decade. My experience in consulting is trying to solve the problem with the simplest possible technology, not seeking technology for the sake of technology, but really trying to put it together to solve the problem. And that type of experience has led to me writing a book on feature engineering, which I will speak a little bit more during this talk. All right, so what do we talk about improving the input? Yeah, you may have heard this poem made. It's a wonderful poem, but it was also quoted on the movie Interstellar. Do not go gentle into the good night, rage against the dying of the light. So for us, data scientists, we receive some data, and that's the definition of our task. And we tend to take that data in a very coy, willing manner. But no, we should rage against the input data. Yes, we should seek to understanding and find errors. Yes, and then go back to the source of the data and question those errors and try to understand the process that produced the data. See, these things are really related to the whole larger organization and the people involved. The data itself is not going to tell you the process that created it. Yes, and that's where a place where we can make our human side count. This in turn means that once you have this data, you may seek out to expand it. A lot of work normally is put together to reduce the number of features, to reduce the type of data that is being used by the model. And that's true. In general, having too many features leads to poor quality models. However, many times a few extra features of key value can make a big difference in the success of a system. That includes computing things from data you have. Yes, if you believe that getting a ratio between two features is important, that can make a big difference because many models have for example, neural networks have very hard time with ratios. And in the same way, techniques to detect missing data and find appropriate values to fill it in. Another source that is normally missed out is to expand the feature using external data. In one of the case studies in my book, for example, we use a list of cities to give context to GPS locations. So instead of using the GPS locations directly, we transform the features. We transform the features into distances to these different cities. And that way, I mean, the input data didn't have information about cities, but we know that the cities that are around the map might have value to inform the classifier. This type of decisions cannot be done automatically by a machine learning system, or at least doesn't look like they will be able to do so for the next decade. In the similar vein, if you want to improve the data to your system, you can improve methods to handle missing data. Missing data is very, very common in production systems, and many times the toolkits we use don't handle them properly. Yes, for example, in some toolkits, the missing data is going to be just replaced by a zero. Yeah. In general, you want to improve the missing data by imputing. That is, by finding a value that is as inconspicuous as possible, that the machine learning will not use that value to drive the decision. In the most complicated case for imputation, you will train a full classifier just to predict that missing value. But in the perspective of a human working with the data, the fact that you have missing data indicates that there's something about the process that generates that data that we need to understand better. Yes, is that data missing because, for example, the system that produced the data changed over time? That might mean that you are working with historical data and, surprise, your system no longer produces that data either. Yes. Conceptually, many times people said, I'm giving you this data to build this system, but that doesn't mean that that data is the data they are collecting right now, because the system just changed and uses a different data in a different format. The second issue is you may decide to deal with missing data by saying, oh, I only have a few rows with missing values. I'm just going to remove them. Now, fast forward into the output part. If your business requires you to produce an output, even in the case of missing data, then you will have a system that is unable to do that. And you don't want to have a system that says, oh, you are a valued customer, but your sales contact just quit the company, so we cannot provide you any recommendations for purchase, because with that missing data, our system cannot operate. that will be unacceptable. So every time you have missing data, that means that this is a moment to stop the algorithms and start the questioning. And now the other option is to focus on the output. I believe you have a talk this morning that discussed that quite a bit by Annie Ying and her group. So in data science, many times we train models and evaluate it over held out data or faults, yes? And there we have a substantive question to answer that drives our the success of the enterprise. Which metrics do we use? Yes. And I mean, 99 out of 100, everybody just uses the metrics provided by ML toolkits. The better the metrics, the ML toolkits, maybe the richer the outputs, the metrics people use. But that's really unacceptable, right? You are letting these people who wrote machine learning, generic machine learning toolkits, decide a key piece of your whole process. Yeah. Instead, it makes much more sense to involve the users of the system and help come up with a custom metrics that really finds the use cases intended for the model. And quantitative metric is not the only way you can evaluate how useful a model is. You can also do a qualitative evaluation. And in the agile mindset, this is a great moment to engage the end users and discuss any improvements. So, as I was mentioning, metrics seldom align with business needs. And again, trying to find a way to make your human side count. Computers are very hard to optimize multi-objective functions, but humans are very good at this. In reality, most of the things we do in life are exactly that. Work-life balance, politics, etc. These are all multi-objective functions. As an example, when I was working in question answering, we used a tool that computes 36 different metrics for a run of the system. And say, well, this is question answering. What other metrics you may have beyond, did you answer this right or wrong, correct? But no, there were some rather exotic metrics, like, for example, the average of 1 over R, where R is the rank of the first correct answer in the list of return answers. So these type of metrics were actually very valuable to try to understand the type of error the system was making and to compare two different variants of the system. And therefore, in a way, the takeaway from this talk is your Jupyter network, Jupyter notebook is not going to jump into WebEx and start talking to people, but you should, yes? So a big example of an improved output is to say, the person is asking me for this, and this is very complicated. Now, may I be able to solve a relaxed version of what they are asking, and that will be even more useful for them. We don't know until we ask. The case in question answering is this possible for the system to just answer, I don't know, as a valid answer, yeah? And in many cases, when that's possible, the system switches from being a full question answering system to trying to tune this threshold parameter to decide in which moment, which setting it produces the most quality output. And in many business situations, this possibility for the system to say, I don't know, make it a much more useful system than ones that always give you an answer, irrespective of whether it's correct or not. And we are very used to the phrase garbage in, garbage out, yes. But in the same fashion, what you choose to improve is also what you get. You may get good quality data in, but if you are seeking to get garbage out, you're going to also get garbage out, irrespective of whether the data is high quality. This is very, very common in the very common discussion in management and business settings. You may have heard the case that in colonial India, the British wanted to get rid of the snakes or the cobras, so they start paying people per killed serpent. Well, people then started breeding the cobras to get this cash reward, and then the overall population of cobras actually went up. And this is also similar in many startups that they use what they call it vanity metrics that always increase, like total number of visitors. So we collectively as data scientists spend a lot of time building system, training system, and evaluating them, and very little time discussing which metrics we use to evaluate, when there is plenty of value there that we miss to tap many times. And in a way, it will be very rare that a quality metric that has an impact on the whole thing is already readily captured by some number that you obtain from scikit-learn. So at the beginning of this talk, I mentioned about AUTOML, and I'm not so sure how many people are familiar with AUTOML. The idea of AUTOML is that, well, if you are training a model, you have to choose the model and its parameters, and that's what you do as a data scientist. Can just a computer do that? Yes, and yes, the computer can do that. The issue is that the search space is huge. Yes. On the other hand, the type of problems we are trying to solve in data science, particularly at the enterprise level, are very similar. Therefore, as human problems tend to be similar, that helps constrain the search space enough to be treatable, at least for some cases. And besides, well, searching these large search spaces involve a lot of computational power, but computers are becoming more and more powerful, not necessarily less electricity hungry. And in general, AUTOML involves then the ML machine learning process for automating real-world applications. You try to automate data preprocessing, feature engineering, model selection, hyperparameter tuning, and checking automatically certain type of problems. It is very likely that you have already engaged some AUTOML in this most reduced way as using a grid search in scikit-learn. In this case, this little example, we are trying one kernel, 2 different parameters for the kernel, and then for a different type of kernel, other parameters, and this lines of code just checks all these possibilities. All right, so one of the reasons I feel compelled to give this type of talks is the fact that data science many times bases itself on a machine learning tradition. And the machine learning people, the researchers, have the idea that humans shouldn't be involved in any of the decisions because they are more interested in making a hard AI system, a system that emulates human intelligence. On the other hand, I see data science and this type of applied work more as an extension of programming. Yeah, so before we program just with code, now we program with data. But because we are inheriting this bias from the ML researchers, then we try to build systems that are completely with any human poisoning with their own ideas, the system. And to me, that's a mistake. We are leaving a lot of performance in the table, behaving in a way like if we were trying to write a research paper. But we are not in the business of writing research papers. We are in the business of trying to make the solution for this a particular problem the best. So from that perspective, given the fact that data science has become a thing, now the ML researchers are actively working in not making it a thing anymore, and using AutoML to completely obliterate what they call ROG ML. Yeah, and this is a very, very similar situation that has happened in artificial intelligence all throughout its history. There was a time, like in the 60s, where search, like I find a string in a document, was considered AI. Yes, these days nobody will think that's AI. So in the same way, I see data science moving towards something that is no longer consider ML or AI, but it has to stand on its own. And to stand on its own is going back to our human roots and solving problems. And that brings us to this thing of domain dependence. Yeah, we need to talk more with the subject matter experts. Yeah, and because if you want to go really fast, you have to ask somebody who knows the way. Yes, and many of the data sources we are working with in the organizations we are, there is people who have spent their career working with them. That type of domain expertise can make a big difference in terms of solving problems. So you need to know the context around the data. And in a way, this is as a concept I'm trying to develop a little more of late, but this idea of speaking data is similar to learning a new language. You know, the difference between translating in your head rather than speaking it. And this intuitive behavior arrives over time through repeated exposure. If you work a lot with a certain data set, then you will start speaking that data set. And this is very similar, this type of data set expertise is similar when people go to see a doctor. Yes, when somebody goes to see a doctor, there are actually two experts talking there. The doctor is an expert in medicine, but the patient themselves are experts on their own body. Nobody knows your own body better than yourself, right? So nobody knows your phone access data better than yourself in some moment. That's a little bit the idea. Once you have this type of intuitions and how can you profit from them, there are multiple ways where this type of expertise can be incorporated. My take, of course, quite unsurprisingly, is to use feature engineering. And I define feature engineering as a process for representing a problem domain to make it amenable for learning techniques. And this process involves initial discovery of features and their stepwise improvement. And this stepwise improvement is based on domain knowledge and observed performance of a specific algorithm of a specific training data. And feature engineering can overfit terribly and harm your whole ML process. So I advocate using data in stages to avoid that. And when you start the feature engineering process, and you take all your raw data before you featureize it, and you split it to do a last evaluation at the end to make sure that you haven't overfit the whole process. And in each of the successive cycles, you iterate over the whole ML cycle of train, test, and evaluation, making modifications to the featureizer. And hand in hand with this talk, I advocate for a human-in-the-loop process for feature engineering. And it hinges on two key analyses, an exploratory data analysis and an error analysis. We'll discuss them in turn. The exploratory data analysis, you analyze the data sets to summarize their characteristics and make hypotheses about the data. So I help you pick a model and an initial featureization. How you do the exploratory data analysis every time you receive new raw data. It is very tempting when you receive raw data to just jump immediately to build a model. That is quite valuable to actually spend some time visualizing the data and understanding it. And also, it is useful to do some error EDA over time to detect whether there has been drifts on the data. And if the hypothesis you use no longer hold, that might mean that you may need to retrain the model. How to do EDA is very data dependent. The topic is normally taught in statistics courses. You can gain some insights by running a battery of common statistical tests and characterizing the distribution of the data. For examples in the context of data science, my book has open source code that contains multiple examples of EDA over graph, text, image, and time series data. In general, the EDA is much more code many times than the actual model building. For the open source examples, I build a data set from Wikipedia that help predict the population of cities and towns using properties, textual description, satellite imagery. And an example of EDA, for example, over text. So take a sample of Wikipedia pages and look at the way the population is expressed in the different pages. And from there, then we can make some hypothesis about the type of featurization we might need. So that's at the beginning. While you are doing the feature engineering, then you profit from doing an error analysis. And the error analysis you do for feature engineering is different than the evaluation of the whole system that normally look at aggregate metrics. For feature engineering, you want to find individual instances that are representative of large classes of errors, normally using a contingency table, and you have to have the system instrumented so you can go back from these classes to the instances that generate it. And from there, you can drill down on hypotheses for reasons behind the error. And then you can see whether those hypotheses actually are presented enough so you don't over-engineer. As I mentioned before, well, error analysis is a great moment to involve future users of the trained model because their feedback can go beyond the model itself. And many times you may find out that you are building a model for the wrong problem. Yes. So, and communication is much easier with end users over a trained model. So the error analysis that comes from the examples of my book involve things like realizing that a very small town has the word cities in there, and that is confusing the system. But the type of visualizations you do for error analysis can be quite involved. For instance, to analyze how the data changes over time, it is useful to do this type of visualizations with colors that indicate whether the features have increased or decreased or has been missing for a particular section of the data. All right, so to conclude, in the book Rules of Play, the authors discuss that when you have a game, yeah, you have multiple layers, yeah, multiple layers of rules. You have the rules of moving the chess pieces. You have the rules for playing a certain opening, and you have the rules for playing with your father on a Sunday morning. In that sense, it's type of like layered of rules, yes, of behavior. Machine learning and data science are similar. Yes, you have you start mastering the machine learning cycle of training, test, evaluation. And on top of that, then you can start adding things like a feature engineering cycle. And on top of that, you can start adding things like involving improving the input data or improving the output. Yeah. So to me, from that perspective, to make your human side count, it is better to do this process iteratively, starting from an exploratory data analysis and then performing an error analysis after each iteration, everything with a human in the loop approach, and tapping on domain experts to go faster and achieve better results. And well, this is the book I wrote. It was published last year on Cambridge University Press. It comes with 10,000 lines of Python, and I very, very interested about the topic of how to model the career, the long-term career of people in our field. So I'm very happy to discuss about this further. Let me go back to the chat.